The bits and bytes are a concept that came to revolutionize a lot of fields. One of them was the music industry. In the late 40s, the American mathematician John W. Turkey was responsible for creating the concept of a bit, which is an abbreviation for binary information digit. After that, the use of bits and bytes is essential for data transfer or storage in the digital world. The first form of a bit we had in history is the IBM vacuum tube, which was a way of operating basically like a switch. If there is electricity on it, it's on. If there is no electricity, then it's off. These two states are the first representation of what binary code is. When someone wants to give orders to a computer, the computer registers these orders like codes. But in order to understand these codes, the computer needs to translate them into binary code or bits. A bit can either be 1 or 0, and these values equal 1 on and 0 off. If more information than a bit is required, then a byte can be used. A byte is equal to 8 bits, and although it also uses 1 and 0, the value of a bit inside the byte will change depending on the position. If we think of each digit as a box, each one has a value to the second power, and the more boxes we add to the left, the larger the values are. The first box equals 1, the second equals 2, then 4, 8, 16, 32, 64, and 128. And with this system, a lot of numbers can be represented depending also on the amount of 1 and 0 we have inside a byte. To find out what the number is, the computer has to add up the numbers of the boxes that are on. So if we have a byte that with all the 8 boxes on, the number will be 255, which is the maximum a byte can reach. In simple words, if you have only one bit, you have just 2 possible outcomes. But if you have more bits, the number of outcomes increases exponentially. With this system, a computer can store data and transform it into characters such as letters, numbers, emojis, or anything you can see on your computer screen and hear through your speakers. Depending on the kind of data the computer has to store, it will use a larger number of bytes. For example, for a letter, it would only use a byte. For an emoji, at least 4 bytes are needed, and to store music, you will need a lot more bytes. This is why we have other terms such as kilobytes, megabytes, gigabytes, terabytes, etc. This way, we do not have to say that something weighs 3,300,057,443.2 bytes, and we only have to say that it weighs 3.2 megabytes. But as it was said before, storage is not the only use that we have bits. Bits are also used to describe resolution. In computing, the numbers and units we use to describe resolution can be really lengthy, so a simplified nomenclature is used instead, just like we use cm to abbreviate centimeters. So instead of saying this audio file contains one of 1677216 different amplitudes per sample, we just say it's a 24-bit audio file. Basically, more bits equals more resolution.
Let's do an example. Open up your DAW, take a virtual instrument, and lower the resolution. You will notice that the fewer the bits, the worse the audio quality is. When it comes to recording in a digital system, the computer has to take snapshots of an analog signal to transform it into a digital one. Think about it as a stop-motion movie, where a lot of photos are put together to create a video. The more the photos, the smoother the video, or in this case, the audio. When you want to record audio digitally, the waveform needs to be quantized. That means that we have to assign numbers to the amplitude. This is what we know as sample rate. The most common sample rate is 44.1 kHz. You can find it in CDs or MP3 formats because it is enough to capture all the spectrum of human hearing. 44.1 kHz means that we have 44,100 snapshots in every second of audio, where we have to assign numbers to the amplitude. But there is another factor that determines quality in audio, which is the bit depth. The bit depth determines the amount of possible amplitude values we can record for each sample, or simply determines the dynamic range of your audio file if you want it in English. If your DAW is set to record at 24-bit, then it can take the snapshots of the incoming audio with more accuracy than if it were set to record at 8 or 16-bit. The difference is about millions of snapshots, so the higher the bit depth, the more detailed the recording will be. The bit depth and the sample rate are different things, but they are strongly related, because the number of values are determined by the bit depth. 16-bit has way less number of values we can pick from to assign to the amplitude than 24-bit or 32-bit. Besides, there is always going to be some sort of rounding error when quantizing, but this error is going to be lowered in higher bit depths, because they have a lot more values to pick from. And this is very important because the lower this quantization error is, the lower the resulting distortion becomes, because it lowers the amount of white noise that is also added to the signal. With these two factors, now we can calculate the bitrate of any music format available on the market. Having in mind that most of the storage formats such as CDs have a sample rate of 44.1 kHz and are recorded in a stereo format with a 16-bit resolution, we just have to multiply the sample rate by 2, which is the number of channels in a stereo file, then by 16, the bits of resolution, and the result is 1411 kilobytes per second, or simply 1.4 megabytes per second. But everything changes with MP3. Because these kind of audio files are usually compressed, you can find MP3 audio files with a bitrate of 16 kilobytes per second to 320 kilobytes per second, which is the highest level of bitrate supported by MP3. Also, an MP3 audio file only stores 9% of the data obtained from the original source, and the other 91% is thrown away. This can be translated into a loss of quality that just becomes worse as the bitrate decreases. Now you have an example of the different bitrates in an MP3 audio file.